Hello, my name is Jessica Groven, and welcome to my presentation, Life Expectancies and the Theory of Blue Zones. In this presentation, I will share top findings from my machine learning exploration of global life expectancy data. This research is done in the context of blue zones as an assessment of how credible the theory is. Life expectancies increase globally. Oops. Life expectancies increase globally by steady rates each year. But viewing rates by country reveals wide gaps and differing rates of change across the world. Since the year 1900, global life expectancy has increased from just 32 years to 71 years in the year 2021. That's a 220% increase. While it's important to understand why humans are living longer now than they have in the past, we'll get to that, understanding life expectancy is important for planning our world. As life expectancy grows, the population shifts older, and many of our industries may also need to shift to accommodate this change, like food production, healthcare, and housing. Now to blue zones. The concept of blue zones was introduced back in 2005 to identify places where more people are living to the age of 100. The theory accredited these long-living communities to several factors, including lower chronic disease rates, limited alcohol consumption, and largely plant-based diets. There are lots of debates about the soundness of this theory. Critics suggested that the data was biased and inconsistently recorded, and one even called it cherry picking. The goal of this research is to produce models that can predict whether countries have low or high life expectancies, identify common features in countries with low and high life expectancies, and explore patterns associated with high life expectancy change. By exploring these three goals, the project will ultimately assess the validity of the blue zone theory. Understanding patterns and impacts in life expectancies should be valuable to several groups. A country or organized leadership may hope to cultivate a healthier, longer living population. Understanding trends in this data may help to implement measures to encourage growth in their own region. Life expectancy studies may also be interesting to individuals trying to extend the longevity of their lives now. While this study focuses on national measures, many of its findings can be implemented into daily lifestyles and habits. Let's take a look at the data. The data for this study was collected from World Bank, an organization focused on fighting poverty and providing assistance for economic development. World Bank has collected all sorts of health, economic, and resource data globally and provided it publicly as an API. The data for this project focuses on a few key topic areas: life expectancy, public health conditions, government expenditure, income, alcohol consumption, and chronic illness. Sorry about that. Many of these overlap with pillars of the blue zone theory. We've also included some areas not mentioned. All right, before diving into the analysis, there are a couple of helpful trends to establish before getting into the modeling. First, there is a wide range of life expectancy changes across the world. Since 1960, China is the top growing life expectancy, raising their age by over 45 years between 1960 and 2022. The lowest range in life expectancy in the same time range was Ukraine, who actually lost a year off of their life expectancy. Both of these demonstrate a key behavior in the data. The largest growth is seen from countries with lower starting life expectancies, and the higher life expectancy countries, predominantly the wealthier ones, tend to stall in their life expectancies. Ukraine had a very high life expectancy already in 1960, so the loss of 1 year is still very high. China was in the midst of the Great Leap Forward famine, which was a huge push to industrialize the country, which led to a massive food shortage and starvation. Understanding this basic trend will provide us some context for the results ahead. Many machine learning techniques were implemented in this research. I'll be highlighting some of the most notable outcomes over the next few slides. Our first goal was to project whether countries had high or low life expectancies based on their features. Several classification methods were trained. Models utilizing the quantitative data tended to perform better than models where the data needed reformatting or binning. The Gaussian naive Bayes classification performed well in labeling the countries with low, middle, high, and high life expectancy. The model trained on data surrounding alcohol consumption, cause of death by chronic disease, prevalence of HIV, open defecation, safe water, sanitation, and government spending. With all of this data, the model was able to perform with 84% accuracy. There were high life expectancy countries in the model that were classified as low. This is a pretty extreme error. Decision tree modeling was an improvement over the Gaussian naive Bayes model. The standard decision tree model performed at 89% accuracy, using the root node of death by non-communicable diseases. Government spending per capita, open defecation, prevalence of HIV, and mortality by chronic disease were also important criteria in the decision tree. The decision tree modeling was followed by random forest modeling, which is where many decision trees are trained independently. Excuse me. All right, very sorry about that. In random forest modeling, many decision trees are trained independently, and then data is classified by each model, and all the models vote on the most popular class to be assigned. Random forest only improved the accuracy of this model by 1%. The best classifying method identified with support vector machines. Support vector machines work by finding a dimension space where the data can be separated into classes by linear division. SVMs can use a linear, RBF, polynomial, or other kernels to project the data into higher dimensions to improve this division. The model using the linear kernel performed the best with an accuracy of 93%. The image shows a two-dimensional representation of this division, using features we've already confirmed are important to the classification. RBF and polynomial kernels were also used to train models, resulting in accuracies of 92 and 89%. Through these models, we've demonstrated that we are able to predict life expectancy levels and identify key distinguishing features, but we're still looking for associations with changing life expectancies. We can address that through association rule mining. The dataset was transformed into a categorical dataset, converting each quantitative variable into lower, same, or heightened levels of each feature between the year 2000 and 2020. Association rule mining was then deployed to see what features commonly appear together, and specifically what features appear associated with high and low changes in life expectancy. High change was associated with low starting life expectancy, low income, heightened access to safe water and sanitation, and lowered prevalence of HIV. Low change in life expectancy was associated with higher starting life expectancy, same access to sanitation and safe water, and high income. Throughout this analysis, we had three goals in mind: predict, identify features, and find associations. Machine learning was able to achieve each of these. The models were able to predict countries with high and low life expectancies based on the information provided. Low and high life expectancy countries differ by number of deaths by non-communicable diseases, mortality from chronic illness, government spending per capita, and prevalence of HIV and open defecation. High growth in life expectancy is linked with lower HIV rates, increased access to safe water and sanitation, and lower starting life expectancy. All of these points to say the blue zones theory appears partially confirmed by this project. Of the three pillars of the theory, low chronic disease rates were supported to be linked with the blue zones. Lower chronic disease mortality was a characteristic of higher life expectancy countries. Plant-based diets, unfortunately, could not be assessed. It's challenging to summarize a country's diet. This data wasn't available. Lower alcohol consumption as a factor of blue zones was not supported. In all the testing and modeling completed, lower alcohol consumption did not appear to be a high impact factor in the life expectancy or changes in the life expectancy. Importantly, indicators of public health measures, government expenditure on healthcare, and income levels are left out of the blue zone theory, but were heavily influential in our analysis. This leads to a lukewarm assessment of the blue zone theory. There are parts that agree with these findings, parts that conflict with these findings, and there's findings that are excluded from the theory. One challenge in assessing the blue zones is that they are usually limited to small communities and towns. Generalizing to a country level, where this data was available, may have been too broad of a stroke to identify key nuances in the blue zones. One small community with a specific pattern might get lost on a larger sea of towns and cities that make up a whole country. Additional data on diet and exercise would pair nicely with the analysis completed so far. This would help to assess the third key pillar of the blue zones and take this project to additional insights. Thank you for listening.